field. So J is my current density. So this equation now is an exact equation of motion at the macroscopic level. And then you want to associate to every such conservation law the optical conductivity sigma of omega. So we all remember from the textbook, in the case of the famous Fourier law or Fick law or Ohm's law, this is the same law, just with appearing just in different contexts, that if you impose a gradient of some potential, here denoted by gradient V, that this will induce a current, and if this force that you applied is sufficiently small, there will be a linear relation between the two, and the proportionality coefficient is what is by definition conductivity. And then in general, this is some function that depends obviously on frequency omega of your perturbation. And generally you can split it into two parts. So sigma reg denotes the regular part, and then in some cases there will be a delta peak at zero frequency with a coefficient called calligraphic D, and this I call the Drude weight. I mean, this is known as the Drude weight. And if the Drude weight is non-zero for this particular conductivity, it means that there is some dissipationless transport that remained. And this is indeed what happens most famously in non-interacting systems, because there is no scattering mechanisms, and so if you establish current at the beginning, it will flow forever. It will not dissipate out. Now it would be nice to have like a framework which allows you to efficiently compute such a quantity, but in fact turns out to be very difficult. So of course, numerically, you can develop methods to approximate such quantities for various classes of models. But so far the analytic approach goes, it's actually out of scope at the moment. But what one can do is one can just look at the zero frequency limit of this conductivity, and that will be called the DC conductivity, and that's a quantity that can be accessed within hydrodynamics, as I will show you shortly. So I forgot to say that if there are some questions along the way, please feel free to interrupt and ask. Okay, so how to compute this conductivity? So if you open a textbook by Kubo, for example, which is how I back in the days how I started learning about this field, it will tell you that you can express these conductivities by integrating the current correlation function. So this is just the time integrated current correlator at beta some inverse temperature, and C stands for connected correlator. So this is the object of interest. And now what happens generically is that this quantity, this is some finite quantity, and this is the number that you would like to get. But on top of that, transport, or like let's say normal transport, by which I mean diffusion, requires a little bit more. So let me also remind you of the diffusion equation for a second, because diffusion equation is that's what by definition diffusion law means, right? What by definition it represents. So it's this simple linear PDE, which you can explicitly solve, and you can represent this dynamical two-point functions of a field phi, and it will be a Gaussian, right? It will spread as a Gaussian. And so when I say normal diffusion, actually what I have in mind is that not only the conductivity is finite, which by virtue of Einstein relation implies finite diffusion constant, but also that this so-called dynamical structure factor is asymptotically Gaussian. Okay, so at finite time it may not be Gaussian, there may be deviation, but at large time you need to relax into this Gaussian shape. So that's what I mean by normal diffusion, and any law, transport law that is not that is anomalous. So I just want to clarify the definitions, and these are my definitions, also definitions that many other people use, but they are not universally accepted definitions. Sometimes people will say law is diffusion, but they will show you something else which is not a diffusion, then it becomes confusing. So this is why I want to fix my nomenclature at the beginning. So, and then you may ask, okay, if a law is not diffusive, how to characterize it then? And you can still stay at the level of these dynamical structure factors. And then you can ask, like, if you take the second moment of this dynamical structure factor, how does it behave at large times? So if the law was normal diffusion, then you would scale as 2 times d times t, and d will be some time-independent constant, namely the diffusion constant. But if you have a spreading that is, for instance, faster than diffusion, which is called superdiffusion, then you can think of this d as being time-dependent function. And then in general, you can introduce an exponent alpha over here, and you can say that this variance goes as t to the alpha plus 1 at large times. And now, as I said, if alpha is 0, you have normal diffusion. If it's 1, right, it means it would grow as t squared, and that would be ballistic transport. This, for instance, what you will find if you take a wave equation. But if it's between 0 and 1, then you will call it superdiffusion. And alternatively, what is also very conventional is that one defines this characteristic length scale as being a time-dependent length scale that grows as t to the 1 over z, and then one defines this z as a dynamical exponent. So I will mostly use this z, not alpha, and the relation between the two is simply written as this one. You see my cursor, right?
Yes.
Yeah, great. I just saw. So cool. Okay, so now I want to give you a brief history of superdiffusion. So I will be interested now in a particular occurrence of superdiffusion, which happens in integrable quantum chains. And this is actually something that goes back to a paper by Schneiderich, which I believe was published in 2011, so it's been 10 years, where he first studied spin transport in quantum chains with the method of Limlat reservoirs. And actually, he already found back then that there is an interesting anomalous diffusion law with this fractional exponent z equal 3 over 2, which takes place in the isotropic version of the Heisenberg spin 1/2 chain. And then shortly afterwards, there was a similar experiment. So these are all now numerical simulations, right? I have been hearing some sound. So late afterwards, there was a paper by Junkovic and Prosen who found the same behavior with the same exponent, also in the classical lattice discretization of the Landau-Lifshitz model. And then for some number of years, there was not really any interest in this problem until a few years back when they revisited the problem with the state-of-the-art DMRG. And they found, again, a much better and clear signature of this anomalous transport law with exponent 3 over 2. Interestingly, in that paper, this Nature Communication paper, they did some analysis on the stationary scaling profiles of the dynamical structure factors, and they concluded in favor of the rescaled diffusion law. So just a diffusion law with the rescaled time variable, which turned out to be incorrect, as I will tell you in a second. So here I just included 2 plots from that paper just to give you some feeling what is happening. I have a phone over here, which I will happily ignore. Sorry for that. So there are 2 plots. The right one is for the anisotropic case. So you have this delta anisotropy. You put it to some number larger than 1. And you find, so what is here plotted is the current density. You can plot the magnetization density or the current density. So the experiment works like this numerical experiment. So you take 2 thermal states and you basically split it into 2 halves, and then one half you polarize slightly positively and one slightly negatively. You touch them together at time 0, and then you observe what happens. So something will happen in this, let's say, light cone region or this interface region, and then you want to see how does the current build up in this region. So on the right plot where there is anisotropy, you can find that the characteristics x as a function of t will be x proportional to square root of t, which is what normal diffusion gives you. Whereas on the left picture, which is for delta 1, so for the isotropic case, you see that it's far more broad. And actually, you will find that, and you see that it's not a full light cone, right? So it's It's not linear, but it's faster than diffusion. And actually, if you feed the characteristic, you will find that it grows as t to the 2/3, which would translate to this exponent z equal 3/2. So the mistake that I mentioned about the conclusion was then shortly afterwards fixed in a subsequent paper, where they did some more elaborate scaling analysis. And actually what they did is that they found that they constructed a discrete time integrable version of that model, which is much more efficient to simulate. And they were able to discriminate between the Gaussian and the KPZ. And so here is just one plot from that paper. Maybe it's not so important what are these quantities that are plotted, but basically the dynamical structure factor in an appropriate scaling variable is presented either by the red curve or black dots, depending for which model. And then the green curve is the Gaussian fit, and the blue one is the KPZ, so the Kardar-Parisi-Zhang universal function that I mentioned at the beginning. And this is, it's a fairly good, but not exceptionally good fit, which kind of shows that the KPZ might be the answer. Certainly it's not a Gaussian, so importantly, this rules out any normal diffusion, or a scale diffusion rather. Okay, so that was for the introduction. So now the question at this stage was how to explain this phenomenon. So at that time, this framework of generalized hydrodynamics already existed, but it was still in its infancy, let me say. And then the name of the game was to explain this phenomenon within this framework. So what is generalized hydrodynamics? So very briefly, you can think of it as a universal hydrodynamic theory, which applies for integrable systems, or more generally, it works for any system of interacting quasi-particles that can be described by completely factorizable scattering matrices. In other words, that undergo completely elastic scattering. So completely elastic scattering, what do I mean by that is you have not only conservation of energy and momenta of your quasi-particles, but indeed you have that the entire distribution, the entire set of quasi-momenta of quasi-particles that enters in the scattering region comes out, leaves out that region unchanged. So, and this is a very special constraint on the scattering matrix, and it turns out that integrability, basically, it's pretty much synonymous to this condition. So you will have it in some very simple classical systems, such as elastic hard rods that have been studied decades ago, or some simple soliton gases. Then you will have it realized in completely integrable partial differential equations or difference equations, such as those that I listed up here. And then most famously, perhaps, are the Young-Baxter integrable systems, so either quantum integrable spin chains or quantum field theories. So for all of these systems, one can apply this in generalized hydrodynamics. So what generalized hydrodynamics does is just hydrodynamics, which means it's an exact theory that governs large-scale fluctuations of equilibrium states. But here it is adapted for the situation where there are infinitely many local conservation laws. So due to integrability, you will have a long list of local conservation laws, and for each one of them, you write a continuity equation, and then you average on equilibrium states. So these brackets means averaging as usual. And then what happens is that the expectation values of current densities, there are some complicated nonlinear functionals of the charge densities Q, but nevertheless, what exact functional this is, it's known because you know from integrability, you can basically infer it. So that's what's important. So there are some caveats maybe I want to mention first. So if you write it in this form, it's not a priori clear which conservation laws one should include into this list. Now you can take an effective approach and say, I will just include n of them, right? And then forget about the rest. But obviously this is dangerous, right? You are neglecting potentially relevant hydrodynamic modes. So this is some kind of a cutoff in your hydrodynamics, and you don't want to do that, especially if you're after this type of questions that I want to address here. And particularly what is important that this conservation laws need to also include the quasi-local charges that turned out to be very important in a different albeit related context of quantum quenches when people studied thermalization from quantum quenches. So these guys also should go to this set of average conservation laws. So now you can ask, well, how do you get access to this thermal averaging? Well, an initial approach would be to physically construct these currents as operators and then subsequently perform averaging on them. This actually has been realized, at least in quantum integrable systems, but relatively recently. So in this paper, they provide a method how to construct these currents and how to average them and all of that. But the outcome of that procedure is something that one may guess straight away. And this is how actually this whole business of generalized hydrodynamics started, with these two papers that I cite in the top. So the key two relations are basically the ones that I write at the bottom of this slide, is that if you take a charge density, so here I for me is just a dummy label, which label charges 1, 2, 3, 4, 5. I'm not telling you what these quantities are. And even going forward, I will not really focus on particular models. So I will try to formulate everything in some abstract terms. So hope that will be clear. Otherwise, please ask for clarification. So take some charge, some conserved charge, and you want to know what is the equilibrium average. So it turns out that if you know the thermodynamic quasi-particle content of that model, then you can get this value by simply taking a charge that each quasi-particle species carry and integrate it over the densities of quasi-particles that characterizes this particular equilibrium state. So there's a bunch of labels here. Maybe I should explain. So theta for me is the so-called rapidity label. Is just a label that uniquely parameterizes the quasi-momentum of a quasi-particle. And A is a label that runs over all the quasi-particle species. So basically, every time when you have to take the spectral resolution, you have a sum over all quasi-particle species, and then subsequently you integrate over the quasi-moment as well. So here there is a label missing in principle on this Q, which I just know. There is a similar formula remarkably for the current expectation value, where you just insert under this integral so-called technical law for that quasi-particle mode, which I will explain in a minute how you get.
The sound is very bad. I don't know. Could people speak up?
I think someone has a mic turned on and recording. So I will just proceed. So okay, so in practice, then it turns out that rather than dealing with the charges Q, it's more convenient to treat as thermodynamic state functions just these densities of quasi-particles themselves. And this is possible because of a duality between these two objects that is known the string charge duality, which tells you that if you know the expectation values, equilibrium expectation values of all the quasi-local charges in the system, this is equivalent to knowing the distributions, rapidity densities of quasi-particles, and vice versa. So there is really a relation between the two. And this allows you to recast this hydrodynamic equations of GHT simply as the equation of motion for these quasi-particle densities. In particular, in thermal equilibrium, there will be just some densities that depend on the mode, on the quasi-particle label A and on beta. But in hydrodynamics, what you do is promote them to a time-dependent quantity by the required. And then again, you have like a continuous conservation of form, and this you will get what is important is that motion of dressing. So, and this is some effect that you will not have in free systems. So we know that free systems likewise characterized by ballistic replicating quasi-particles, but one major distinction there is that they don't interact, and hence nothing happens really. They're transparent, they go through one another, and well, life is simple. So here it's slightly more complicated by the fact that when a quasi-particle is propagated through a background that can be some thermal background of other quasi-particles, every time it collides with other quasi-particles, it gets a bit perturbed, and the effect of that is the bare charges it carry, if it was propagating on top of the bare vacuum, these bare charges get renormalized into the dressed quantity because of this effect of interacting with the environment. So this transformation can be made very explicit, but I will not go into that because then I'll have to explain some notions of integrability, and that's not very important. The main point is that it's fully determined by the many-body S matrix, so more precisely by the two-body S matrix, because the integrability allows you to reduce everything into a two-body scattering process. But you can think of it as a black box. And finally, the effective velocity that I mentioned on the previous slide, which enter in the current formula. So over here, it's none other than just the group velocity of quasi-particles that you obtain by taking the dressed energy and you take the derivative with respect to the dressed momentum of that quasi-particle. So that, what I explained you so far, is basically the main ingredient of this framework. And now, equipped with that knowledge, we can go back and address the question of superdiffusion. So first of all, the first question is, so this conductivity that I defined in the beginning and this transport coefficient, namely the DC conductivity and the Drude weight, is there a nice hydrodynamic representation for these quantities? And as you can see on this slide, the answer is yes. And here I'm just not showing you any derivation, just stating the final result, which is nice because it's universal. So you can take any quantity Q and you can ask what is the associated Drude weight, and all you have to do is you have to integrate over all quasi-particle types, and what you integrate over is the density times the Fermi. So N of A are now the Fermi filling function associated to the particular state. Rho are the density of quasi-particles associated to a particular state. So this is all. There are some thermodynamic state functions that you can derive, and then you multiply the square of the effective velocity and the square of the dress charge, and this is the Drude weight, and that's the exact result. And you can do even more. So you can also get access to the DC conductivities, to the whole matrix of DC conductivities, in fact, which is also known as the Onsager matrix. Then you have to adapt this generalized hydrodynamics in the sense that you have to include the diffusive correction to it. So what I showed you before was just these two terms, which are called Euler scale equations. So you have to add this term. I will not go into that, but actually it turns out that similarly to the Drude weight, there is an explicit exact formula for this diffusion constants as well. So that's what is powerful about this formula. Good. So now to this superdiffusion. So first of all, it's important to stress that this phenomenon only occurs for a particular subset of conservation laws, and these are the Noether charges associated to non-abelian continuous symmetry of a model. So now I'm assuming that I'm confining myself only to systems that possess, in addition to integrability, manifest non-abelian continuous symmetry under some Lie algebra G. And the focus is now on transport properties and transport coefficient associated to those Noether charges. So to do that, we can construct an equilibrium state, a density matrix, which beside Hamiltonian, we also include all these charges when with the associated chemical potentials Hi. So now I just runs over all the Noether charges. Or in fact, what you include in this ensemble are not the Noether charges, are just the Cartan set of the Noether charges. So we have, right, if algebra G, this is rank R, then we have R many of them over here. And then we define this object, which is the dynamical structure factor, but just restricted now to the Cartan sector. And I denote it by Cij. And then we can ask, how does the second moment of this quantity scale at large times? And the coefficients, proportionality coefficients in front of T-square is the Drude weight, are the charged Drude weights, and the coefficients in front of the linear term, are the DC conductivities. So back to these expressions, you can stuff all the data that you have obtained into this formula. And now what happens is something remarkable. So if you see from this expression, one thing is apparent already, is that the Drude weight are manifestly non-negative quantities. Okay, so if you take a generic state and generic quantity, they will be positive. If they are not positive, they can be zero. But if they are zero, there needs to be a good reason why they are zero. And then what happened? This is exactly a situation where Drude weights can be zero, and this will happen indeed only if all the chemical potentials are set to zero. So only in the limit of grand canonical Gibbs ensemble where all the chemical potentials are switched off. By having an exact expression for these dress charges, you can actually show that the limit of these dress charges is zero, and hence all the Drude weights zero. In other words, upon restoring G invariance of the underlying Gibbs state, all the Drude weights in the sector of the Noether charges will identically vanish. Okay, good, you may say, so therefore there will be no ballistic transport, but there will be still, jumping back quickly, there will be still some DC conductivities, or diffusion constant, if you like. So you would expect finite diffusion constant, but what happens is, again, you can write the exact expression for the diffusion constant, which I omitted, and you can plug all the data in. In fact, what turns out that for this particular subset of charges, you can even make this expression nicer and compactify it eventually to the formula that I'm writing over here. So it's again some spectral resolution with this familiar factor in front, and now you are integrating over an absolute value of the effective velocity times some tensor, which you can fix purely from the symmetry, on the symmetry grounds. And then eventually you put final chemical potential and you send them to zero. And something remarkable happens. One finds that all of them diverge. So the situation is the following. So the Drude weight went to zero upon switching all the chemical potential off, and all the diffusion constant blew up. And well, basically with this, you already established analytically why there is no normal diffusion in these models with non-abelian continuous symmetry in these states when G invariance of the state is unbroken. Hope was clear until now. Is there any question? All right. So now before I explain the results of our most recent paper, I maybe just want to briefly go through the previous results, because there was a number of papers before which addressed, which made partial progress on understanding the microscopic reasons behind this divergence. So first, we were able to show, well, basically with the argument that I just presented, that all these diffusion constants diverge, and we were able to show this for the basic case of the isotropic Heisenberg chain, but also for a couple of other models. And already back then, we saw that the reason for this divergence comes from quasi-particles which carry very large, if you think of spin transport, which carry very, very large magnetization. You can refer to them as giant magnons because they have a lot of magnetization. So this will be very large bound states of magnons, if you will. And then afterwards, shortly afterwards, there was an argument by Vasur and Gopalakrishnan how to actually infer this dynamical exponent 3/2 that I mentioned purely on kinematic grounds. And one modification of that argument I will show you in a minute. And afterwards, okay, so then this exponent, there was an argument how to get it out. But the belief was that there is the KPZ universality underlying all this phenomena. So the question was how to explain that. And then for this basic model of the Heisenberg spin chain, there was a proposal by Bulchandani how to actually get to the the Burger's equation, to the noisy Burger's equation, which is written over here, from the microscopic equation of motion of the Heisenberg model. And it involves some kind of particular coarse graining procedure, but the main argument here is that when one considers generalized hydrodynamics in systems with non-abelian symmetries, one has to also incorporate the motion of the pseudo vacuum, or if you will, of the order parameter. And then on large spatio-temporal scale, one component of this order parameter, which turns out to be a composite field, so there is many real degrees of freedom that you may have. So one of these components will decouple, and this component plays the role of this field phi, which is governed by the Burger's equations. And basically how you introduce the noise is purely on phenomenological ground to say that it comes from effectively integrating out the macroscopic degrees of freedom of other modes that are in hydrodynamics. So of course, this approach doesn't allow to tell you and doesn't allow you to infer anything quantitative from it. Then in another paper afterwards, we actually managed, without referring to that phenomenological picture, but working within GHD, we managed to get to this coupling constant lambda of this equation through a particular thermodynamic scaling limit, in which we find out that these giant magnons that I mentioned emerge in this limit as semi-classical solitons that are governed by the Landau-Lifshitz field theory that I wrote over here. It's an interesting story, but I don't think I will go deeper into that today. So that was sort of the state of the art at that point. And on top of that, there was a number of other works which were interested in this phenomenon and addressed it in various models by simply on numerical grounds, and they were able to confirm that this exponent is not only tied to this Heisenberg chain or the Hubbard model, but there is many more quantum models and classical systems, integrable system with non-abelian symmetry that all seem to show this exponent. So at this point, there was a good moment to basically conjecture that there is some universality behind this in integrable systems. But it wasn't really clear still what are the necessary and or sufficient conditions for emergence of this type of phenomenon. What was clear that integrability is important, because if you don't have it, it's gone. But it's not enough, because, for instance, you can take the anisotropic Heisenberg model and it's also already gone. Or in other words, it's immediately regularized to normal diffusion plus the Drude weight. So it was clear that this continuous symmetry, it's important also from the point of view that if you break it with chemical potential, you will again regularize this effect. But what wasn't clear if maybe more complicated non-abelian symmetries can induce perhaps an even richer set of dynamical exponents beyond this 1/3/2. So the two most viable scenarios at that point were that all integrable systems that have non-abelian global symmetry of a simple algebra G will exhibit superdiffusion with the dynamical exponent Z equal 3/2 in the sector of the Noether charges. But if this is indeed true, the question is why? And the second possibility was that perhaps in the higher rank systems, there will be a wider range of dynamical exponents. And this second option was not really was a serious possibility, because indeed there was some early numerical evidence by another paper by Znidarich from some years back, where it shows that in the SU4 symmetric spin ladder, integrable spin ladder, there was numerical evidence in favor of an exponent of 5/3. So, and indeed, some of us believed that, well, some of the authors of this paper believe that it will be there will be different dynamic exponents, and the other believe that that it will be the same exponent. So it was so that was why we're motivated into finding some universal picture behind. So, and then the conclusion is, so now I'll try to just make the conclusion of our paper, which is maybe fairly long and technical. I'll try to compactify it as much as possible. So I'll just go straight to the conclusion first. So indeed, the scenario 1 turns out to be true. So in the models, in quantum integrable models, invariant under non-abelian symmetry groups, you will find a dynamical fractional exponent 3/2 in the Noether sector. And remarkably, this happens irrespectively of which Lie algebra you take. So it can be any Lie algebra from the classical series A, B, C, or D, or it can even be an exceptional Lie algebra. As we know, all these Lie algebras have been classified a century and a half ago by Cartan. Then what you can also fiddle with is what local degrees of freedom you can choose. So you can take any local degrees of freedom which transform according to any unitary irreducible representation. It's still, the exponent remains the same. And also you can have Lorentz invariance or not. So it holds also in integrable quantum field theories which have isotropic degrees of freedom, such as the nonlinear sigma models, the principal chiral fields, and so forth. And because of this unprecedented robustness and inevitability of this transport law, we decided to dub it super universal. So what's important is that for any class that I mentioned here, you can still have infinite freedom of choosing microscopic parameters, and you will still get this law. So the only importance is that you don't break integrability, because integrability is what ensures that quasi-particle excitations are stable against decay. So that you need to make sure. So then you have interacting quasi-particles, and because of the symmetry that you have, the symmetry constraint, it will force you having this exponent. So that's the result of our paper. So now maybe to conclude on 2-3 slides, rather than giving you the Bethe ansatz justification for that, so because we have eventually all the ingredients, the Bethe ansatz machinery is available behind the curtain, so you can of course just go and start cracking. But rather, I'd like to give you some more intuitive explanation, which is using pretty much this dimensional analysis, how to get to these exponents. So, so let's start like this. Let's say that this diffusion constant, which is divergent, let's regularize it. And let's do that by imposing some cutoff in the spectrum. And the cutoff I want to impose is by simply integrate out a bunch of quasi-particles which carry very large quantum numbers. So specifically, it turns out that in the models that we are describing, quasi-particles carry two internal quantum numbers, which I call A and S here. A is associated, well, you can think of it as a flavor. So you will have a bunch of magnons and bound state, and they can be of different flavors. So this is what A is labeling. And if rank of the group is R, there will be exactly R flavors. This is how this is what symmetry imposes on you. And then the second quantum number is S, which tells you the number of constituent magnons inside the state. So these magnons can bind, and they can bind indefinitely. There can be any number of magnons that bind together, and this is called S. So what we are doing here, we're just saying, okay, let's say that we only include S up to some S star. And of course, if we do that, each quasi-particle species, each magnon species will contribute some finite amount to the diffusion constant, but then eventually when we sum everything, it will be finite. So, and then we say, okay, now upon removing this cutoff, S star, how does this divergence, how does it happen? And we can associate to this divergence some exponent epsilon. So that's one exponent that we can define. Then in the time domain, of course, we have the diffusion constant. We promote it to a time-dependent quantity, and then we can ask how does, in this time domain, this diffusion constant diverge. And we say with exponent alpha, which will be somewhere between 0 and 1, right? That we can say, because 1 would mean that it's ballistic, but we know it's not ballistic, so it has to be less than 1, and it's faster than diffusion, so it's larger than 0. And finally, the effective velocities of the quasi-particles need to also have some fall-off with increasing S. And here we associate this, we characterize this by exponent nu, which is some larger than 0 exponent. And now what you can do, you can simply define the associated anomalous length scale to this quantity. And you can see that on the one hand, it will grow as t to the 1 plus alpha over 2, which gives you the exponent z. And then you can also get it by different means in the following sense. So you can, depending on this anomaly length scale, you can talk about light and heavy quasi-particles. So light would be those for which their velocity times t is smaller than this anomalous length scale, and the heavy ones will be the one for which is larger. So for the heavy ones, basically they are big enough, they are effectively undressed. So, and the small ones, you can think of them as being the dressed one. And then upon removing the cutoff, what is happening is that the part of the spectrum of these heavy particles start to vanish, and hence the diffusion, the Drude weight will also start to go towards zero. And in the same time, the light spectrum will start to contribute more and more to the diffusion constant and cause it diverge. And so what we just want to see now is how does, with this cutoff, how does everything scale? And then it's just dimensional analysis. You just relate these quantities, just plugging them into that formula, forget about all the constant, this is not important. And you find two different laws for how this diffusion constant should diverge in the time domain, which allows you to arrive at this nice compact expression for the dynamic exponent z. So now we're able to express it in terms of these two exponents, upsilon and nu, which characterize this and this growth respectively. So as a test, you can now see, okay, let's take a microscopic data of the Heisenberg isotropic sp2 chain, for example, where both nu and upsilon equal 1. You plug it into this formula, and voila, you get z equal 3/2, exactly what happens. So now this looks good, and but one has to be careful here not to get carried away too much, because it may be tempting to say here that, well, pretty much you can now start plugging in any upsilon and nu, and it means that you will have an infinite range of fractional exponents available. But that's not the case. That's not the case. And for the reason for that is that these two exponents are not independent. We cannot assume they are independent, really. They come from some microscopic of your model, and so there will be some relation between them. And one way to see this is, of course, to really take the particular data that you get for these clouds of integrable models, and you will see already at that level that this exponent nu cannot be arbitrary. In fact, needs to be an integer. So, but let's not try to incorporate that information yet. So what you can do is you can, at this stage, you can introduce another regularization, and this time by introducing back chemical potentials. As I said before, this will immediately restore normal diffusion. But this happens in a very particular way. So it turns out that static susceptibilities associated with each quasi-particle mode will have this exponential fall off, and then you can write the formula for this static susceptibility in terms of this hydrodynamic representation. So this is for the static one, and there is a similar formula for the dynamic one when you just insert under the integral the effective velocity. You use the scaling that you assumed before, and then from this argument you are able to deduce that this diffusion, the regularized diffusion constant will diverge with s to the power 2 minus nu. So it's just a different regularization scheme. But then when you combine this with what I showed you on the previous slide, you're able to infer a condition that nu plus upsilon must be 2. So that's already a much more stringent constraint. And then if you indeed look at how the beta ansatz work, what is the particular structure of the scattering matrices in this type of systems, you will see in fact that nu has to be an integer, which means there are only 3 options left actually at this point. So one is that nu equals 0, but that would mean that you will have find a Drude weight at 0 magnetization, which can be analytically ruled out. So this, we already ruled out this option. And the remaining 2 options are that nu would be 1, which would imply upsilon is also 1. This I just show you that happens in the basic case of the Heisenberg model, and implies this dynamical exponent z equal 3/2. And another option is to have nu equal 2, which indeed can be realized, but it should be regarded as fine-tuning, because basically what you have to do, you have to take microscopic interactions such that the magnonic dispersion will not contain the k-squared term, but it will start with the cubic term. See, that's very weird. You need to fine-tune. If you do that, you indeed get a different type of transport law, which also has a divergent diffusion constant, but it has some logarithmic divergence. So if you take away this fine-tuning, that what remains is basically this case number 2, and which establishes why this exponent z equal 3/2 is universal or super universal, if you will. So what we do in the paper, actually, we go further and then we really dig into the beta ansatz and TBA, and it turns out that actually, if you work in the high temperature limit, which is possible in these models because they have finite Hilbert spaces, you can actually even derive analytic solutions to this, to all the relevant thermodynamic state functions, because the TB equations become algebraic. And from these solutions, you can actually infer how the Fermi occupation functions scale at large S. They goes 1/s squared uniformly, and how the total density of state scales, it goes as 1/s, and how the effective velocity scales, it goes as 1/s as well. And then you can plug all this data back into the formula that I show you, and you can infer from there as well what type of a divergence you will have, and basically establish more rigorously this exponent. Final slide. So I present you the argument for this anomalous exponent, but in the beginning I basically tell you that numerics is showing, is indicating that this transport law belongs to the KPZ universality class. And so what we do in the paper as well, we said, let's construct representative examples of integrable quantum chains which have not only unitary symmetries, but also orthogonal symmetries and or symplectic symmetries of higher rank. And then we simulate all the spin chains. So for simplicity, of course, we had to assume that the degrees of freedom transform in the fundamental representation. Otherwise, Hilbert spaces become very large very quickly. But nevertheless, for this set let's say, toy models of each symmetry class, we first check how does the second moment of the dynamical structure factor grow, and we were able to find this pretty nicely, actually, the exponent, the anticipated exponent. And on the other hand, we also computed the asymptotic scaling functions to check whether they have the KPZ form, and here we were not so successful. So this is on the right plot. Yeah, so basically, let me try to remember what we show. So yeah, so basically you scale the function according to this exponent, and then you have to plot on top either the Gaussian or KPZ or something third. And then we had, like, I think we had two different estimators how to one based on the structure factor. I'm trying to remember what exactly we plotted, but I just recall that we had two different methods, which is why there's this gray strip. So somewhere within this gray strip is what you would expect if you had KPZ. Unfortunately, I can't remember what exactly we plotted. But the data that we get is shown in color with different colors for different symmetric groups. And as you can see, the matching is not so good. So obviously at short distances, it's good, but at short distances, you can't tell this apart from a Gaussian or something else. At large distances, is so-so. Nevertheless, just to conclude, we do indeed still believe that it's eventually KPZ. It's just hard to find it in computer simulations, because in another paper before this one, we actually looked into models, into classical integrable models which possess higher rank symmetries, not only unitary but symplectic as well, and there the fit was pretty good. So it seems that in the classical models somehow one can push the simulations a bit further and get more viable data. But this certainly is one aspect that needs improvement, I would say. Let me see. Yeah, okay. So I think I will conclude with this. yeah, I'll conclude here. Thank you for the attention. If there are some questions, I'll be happy to answer. Thank you.
Okay, so if the people ask the question by orally or they send them, you can read the message.
Let me see.
On the left of your screen. There were already a few messages written.
Yeah, but okay, I didn't know it works like that. I'm sorry. I was looking at my slides. I totally ignored what was happening.
Okay, so I think, well, I mean, if people have questions, please ask questions now.
Yeah, please ask verbal questions. I'm not really a fan of this chatting, how to say. Sometimes students do this to me. I really, they write in the chat and then I see it after half an hour.
Well,
no, okay, it means everything was clear, which is super good.
No, for me, not everything was clear. So maybe so the only important thing is how things scale with the size of the solitons. I mean, somehow the number of, I would say, S, this parameter S, which measures.
Yeah, exactly. So indeed, so let me try to make another short summary. So once you have access to the microscopic data, so this will be the data that characterizes your quasi-particles in thermodynamic states, everything is there. Then you just have to analyze how transport coefficients, in this case, diverge, right, by integrating over this data. So then it's just a scaling analysis at this point. So the crucial feature here is indeed, as you said, that the bound state can form, and there should be infinitely many bound states, so they can bind as many times together as they can. And then you can see that when you're taking chemical potential towards zero, most of the spectral weight, if you will concentrate at those type of quasi-particles, so those giant magnons. So they are the ones that cause this anomalous behavior.
And you can
ask, what are these guys? And this is what I just briefly mentioned in one of the slides. So these large quasi-particles, they satisfy an effective equation of motion, which is purely classical and is none other than the classical integrable analog of that equation. For example, in the Heisenberg chain, you will end up with the Landau-Lifshitz equation. And similarly happens in other models. So if you can take, I don't know, SO5 chain, and basically you will find that these giant particles are solitons of the particular Landau-Lifshitz coset sigma model, which lives on, in this case, SO5 mod SO2 times SO3 target space. We also go a little bit into that in the paper. So because there's another aspect that I didn't describe precisely related to this, how do classical degrees of freedom emerge within this quantum spin chains? So because it turns out that all these classical integrable models that do have this phenomenon as well, they are not, they are basically contained within these quantum systems. So perhaps one doesn't even have to do thermodynamics from scratch for this classical system. It's already contained in the quantum one. But this is a bit subtle, so I didn't succeed to derive it.
Okay, thank you. I mean, other questions? Somebody has a question to ask?
Yeah, sorry, I wanted to ask a question. And maybe make a little remark about the giant magnons. In fact, in the literature of ADS-CFT integrability, there are giant magnons, but they are different of those. So some people will be confused.
What are they in the?
They are magnons with momentum of the order of pi, let's say. The usual magnons have a small momentum, but well, that's
yeah. So Indeed, if you want these magnons to satisfy the classical evolution law, they have to have small momenta.
Yeah.
So I think they will be literally what are giant magnons from ADS-CFT literature.
Well, in ADS-CFT, they are. I mean, they have. They are just not bound states, but they are individual magnons with large momentum. I mean, large compared with 1/L, if you want.
So you just take one single quantum magnon and make its momentum small. This is what you're saying.
Momentum large.
Yeah. So, but these guys are then Goldstone modes, what we call.
Okay, yeah, but
right, because
just wanted to say that there is already a terminology about
okay,
and it's not exactly the same one, but it's not very important. The question I wanted to ask is about what's the difference if you start to introduce a small anisotropy. Are these giant magnon solutions still? Do they still exist if the parameter which is related to delta is irrational?
So yeah, so you can introduce anisotropy, and now let's go back to the basic case of the SU2 chain. There are two regimes: when anisotropy is larger or when it is smaller, right? So easy axis, easy plane. Easy plane is actually quite subtle because of this root of unity effects and enhanced symmetry. So let me not go into that, but let's introduce the easy axis anisotropy. Then it turns out that the whole formalism is still there, but the scaling with large S become profoundly different. They become everything becomes exponentially suppressed with this anisotropy. And this changes all the relations, so they will not be algebraic, as I showed you throughout my talk. They will be exponential, and the diffusion constant will be finite as a consequence.
Okay.
So it immediately regularizes everything.
And what about the easy plane case?
Yeah, so easy plane, we have only looked at that case, well, into that for the basic SU2 chain, and their story is complicated by the symmetry that I mentioned. So what happens there is you have the Drude weight even at half filling. So when you switch off the chemical potential, it's still finite. So the Drude weight doesn't get switched off. Then what you can still ask is what are the subleading corrections, and there you can find some anomalous subleading corrections. But it's another complication because then you have this root of unity effect. So it means if anisotropy is cosine of a rational multiple of pi, then you have a finite number of particles in the spectrum, and if it's not, you have an infinite spectrum, and it's super fragile. And there was this story that I was also involved into years ago, which led to this remarkable finding that the Drude weight is not continuous even as a function of anisotropy. So it's everywhere discontinuous effect upon changing anisotropy. So yeah, so it's a whole different story, but shortly, there's this effect of superdiffusion that I discussed today. It's really specific to the unbroken symmetry. So you need to have this isotropic non-abelian symmetry at the level of the Hamiltonian, and even at the level of the state, it must be unbroken. And then you will have.
So this statement about the non-abelian symmetry, do you have a formal proof, or it's an observation for the particular cases that you have considered?
Yeah, so formal proof in the sense of mathematical proof, I don't have. And actually in the very precise word I put it, it's actually not even true. But so there is a bunch of caveats. But basically, let me say it like this, because I don't want to be too confusing. So it's important with what kind of representations of the underlying quantum group you operate. So all these models that we constructed, they basically come from, are associated to Youngians, and in particular evaluation representations of Youngians. So if you do that, then we will imply some particular structure of your quasi-particle spectrum, and within that framework you have this superuniversality. Now if you start cooking up some more exotic quantum group,
let's say quantum affine, some quantum affine symmetry.
Yeah, so I would just say for now, I would just like to have evaluation homomorphisms of Youngians. It can be super Youngians as well. This grading is not so important, but that's what is safe to say. But perhaps it can even go outside of that. That I don't want to say. But yeah, no formal proof. Maybe it.
Yeah. No, thank you. Yeah, I think my questions are maybe too technical, so I will maybe stop here, not to take the time of our colleagues. Thank you very much.
Yeah, you're welcome.
Enej, if there are no other questions, okay.
Enej, hi, Enej.
Ivan.
May I ask you a question?
Of course.
Yeah, I just want to understand one of the slides. You have this global non-abelian continuous symmetry where you have this ensemble.
Let me try to see.
Yes, somewhere.
Where I write that, probably in this slide.
Yes, exactly. Yes. So rho here, I mean, so this QI, they don't commute with each other anymore, right? So how could you write as exponential of sum over QI?
Yeah, so here I only include the commuting ones. The reason being that anyway, I'm interested in the H20 limit where I have G symmetry at the end. So then I can extend this to all the charges. But when I introduce chemical potentials, what you do, you take a maximal commuting set of charges, QI, and you include them here. Okay, so these are just the commuting ones.
Okay, so but in principle, from this Lie group, you can have, I mean, also non-commuting charges.
Correct.
Right.
That's kind of non-abelian hydrodynamics, that you would have non-commuting charges in your ensemble. Actually, I think you could rotate that out, right? So, so if you think of the SU2 case where you have all three components of magnetization, right? So you can stuff it there in the exponent, but then you can rotate your basis and you keep only one direction, and then that direction you proclaim as your new Z.
This kind of determined by HI, right? So if you put some, let's say, infinitesimal magnetization on that direction, so you probably prefer sigma Z there.
Yeah.
No, I'm just wondering because.
Yeah, so normally what I do, I just construct these ensembles when I took the abelian charges, and that's your equilibrium measure.
So in this case, for instance, let's say SU2, you put sigma Z there.
Correct.
Okay. Thank you.
Yeah. Yeah, so maybe one remark which is kind of belongs here is, so this, so what you can do, you can put these charges in the grand canonical measure, but then you don't switch all the chemical potential to zero. Let's just leave them there. And then there are also correlators in the transversal sector. So it means that if you take the basic case, the S plus and S minus components of spin field, you can compute the correlators. And these correlators you cannot access, at least presently, we don't have a means to extract them from generalized hydrodynamics. This is that undular diffusion I referred to. But for me today, that was not relevant because I'm interested in the symmetric case, as I just said. So then all these charges are equal. They can be just rotated into one another.
Okay. I mean, this is very new. I mean, the fact that some KPZ has to do with non-abelian charge. I mean, I never heard of. I mean, before you, I never heard about that.
Yeah. So, I mean, I think what was for me most surprising here is that I think this case of the Heisenberg chain was the first occurrence of this KPZ in a deterministic many-body system.
You were mentioning this very, I mean, I didn't understand. At the beginning of your talk, you were mentioning this very old solitonic model with springs. I mean, I don't know.
Right.
So does it exhibit KPZ, this one?
No, that's a good point. That's Fermi pasta Ulam Tsingu model. Yeah. That's a model of how is it? There are classical anharmonic oscillators, but there is no noise. Yes. So that's deterministic. Yes.
So that's another one, a second one.
Right. But it's a different. So what's interesting, since you made that remark, so you think now there it appears this KPZ scaling here as well. So these guys go into the same box, but they actually don't, because there they explain it on the level of this nonlinear mode coupling theory, which is called the nonlinear fluctuating hydrodynamic. And we know it has been shown that this generalized hydrodynamics is not such. So it has a completely different mode structure and doesn't accommodate for the feature that theory has. So yet again, it leads to this KPZ. So it's a different microscopic mechanism, if that makes sense what I want to say.
Okay, thank you. No other question? Okay, then thank you very much, Enej, for this nice talk. And,
yeah, so thank you too again. And
bye.
Yeah. Hope to catch you soon. Bye.